Good afternoon and welcome to the National Centre for Nuclear Robotics live stream demo event. We are looking to live stream today from two remote locations. We have Professor Mark Hanheider in Lincoln and Professor Tom Scott at the University of Bristol. So first of all, my name is Peter. I'm based here at the University of Birmingham, and I'm basically acting like I'm a base operator that's overviewing work that's happening out there in a nuclear reactive site or a nuclear disaster site, where we're going to send a drone to investigate, to find a radiation source, and then in a separate lab in Lincoln, we're going to actually approach that radiation source using a mobile robot. So first of all, I'm just going to introduce Professor Mark Hanheider. So Professor Mark Hanheider, welcome.
Hi. Pleasure to be here. Really good
Wonderful.
To be here.
So how's everything over at your end? The robots looking like they're about to play ball?
I think the robot over there is hopefully ready to operate in it together with this one on my other side. And we're going to do a bit of a demo of mobile manipulation with some teleoperation in there and some navigation aspects. So bringing together quite a few aspects from our NCNR involvement here.
Wonderful, fantastic. Thank you, Mark. I believe Tom Scott has joined us down below. See if we can just add him to the screen and say hello. Tom, can you unmute yourself?
Hello, everyone.
Oh, there
Hi,
he
Tom.
is. Hi.
I'm wearing my National Centre for Nuclear Robotics T-shirt today, because obviously this is all part of the NCNR programme, which has been a huge success led by Rustam at the University of Birmingham. So I'm out in an event shelter at the University of Bristol's Fenswood Farm, which is a 245-acre facility just outside of Bristol. And at this facility, we have our nuclear robotics test facility. We have a menagerie of radioactive sources that we can use for testing devices. And today we are showing you, courtesy of Suresh, who had a picture there, we're showing you some of the detection capability that we've integrated with the DJI M300 drone system, which is the new emergency response drone from DJI. I'm just going to quickly show you. You can see behind me, this is the M300 system. And as part of what we've been doing, we've been integrating a sensor which is used for security and emergency response applications. This is a combined gamma spectrometer and a neutron detector at the same time. So it detects X-rays effectively, and it detects neutrons. So both of those things are important in case of a nuclear disaster, but they're also really important in case
point has been updated. Please check it on the
that's
map.
the drone talking to me. They're important in terms of if there was an incident, or if someone was smuggling radioactive stuff into the center of a city or another site, that we can use detection technology to detect the radiation, but it has to get close to the radiation source, and we ideally want to do that without people being involved, because you don't want people getting exposed to the radiation. So the system that we've developed just behind me, which will be flight testing as part of this demo, is designed specifically to map for radiation in the event of emergencies. And it's actually just been deployed at the NATO summit that we've just had over in Belgium, as an actively deployed technology that was basically used for security and surveillance whilst the summit was on. But it was used to fly around the building that the summit was going on and the nearby area to map for radiation and to make sure that there were no strong radiation sources either in the area or coming into the area whilst the summit was on, just to keep everyone safe. So the system is the first time that anyone has integrated a radiation mapping system with a DJI drone. Obviously, DJI is a Chinese drone manufacturer. And for this existing system, what we've developed is essentially a small robot which sits underneath and communicates via the Skyport hub to the drone, and all of the telemetry from the drone in terms of the radiation and also the height above ground data as well, which is recorded from a downwards facing LiDAR, is piped straight through the drone's transmission system and comes straight to the handset of the pilot. So this is the sort of handset. And for the DJI, you have two replica handsets, one for the pilot and one for the navigator. And Suresh, if I could just call you in. So I'm going to be flying using one handset, but Suresh will be using the navigator's handset hooked up with an iPad. I don't know if we can see here. You can see that on the iPad, we've got a map of the UK, and in fact, it will find where the system is, and it will zoom in and show us exactly where the drone is. And at the moment, the drone is in my event tent, and we're shielding it nicely, but it's just moved in. We can see we've got a spot on a map, and we can switch in our map between satellite. We can see this is the Fenswood main building, and we can swap to normal sort of Google map, if you like, to understand where we are. And as the drone flies around, we form a snail trail across the map, of which Peter's got videos of that maybe we'll show later, so that we can understand as the drone is traveling what the radiation levels are. And of course, if we fly the drone in a pattern, so a grid, then we can cover quite a large area effectively in terms of searching for radiation. And that has applications in nuclear site monitoring. It also has applications in mineral prospecting, looking for valuable things like gold, which is something I'd love to do when lockdown is eased and I can travel to other countries, to travel to Australia and see if I can go and find some gold in the desert using this exact system behind me. So Peter, I'm gonna hand back over to you for a minute, whilst I'm gonna just take the drone down and prep it for takeoff.
That's wonderful. Okay, can you answer questions whilst you set up at all, Tom?
I can. Well, Suresh, if you wouldn't mind putting the drone out to the side, and we'll get ready for that. Yeah, please fire away with questions, Peter.
So we just have one question, which is how far away can you be from the drone?
We can be as far away as the DJI telemetry system allows. So there's obviously, depending on the country, there are laws as to how far away the drone can fly from you. In the UK, we have to stay within line of sight, which is about 500 meters. But in reality, the drone can send its data over about 5 to 7 kilometers, which is a lot further than I can see the drone system for. And of course, in the event of a nuclear emergency, I want to fly the drone beyond line of sight, because if I'm in sight of the nuclear accident, I'm probably in danger. Something that we've done through the NCNR grant is we've taken this technology actually on a fixed wing drone system, and we've mapped 16 square kilometers of the land around the Chernobyl power plant. And in doing so, we have gone beyond line of sight. And we've shown that in the event of a real emergency, we now have that capability to be able to do that. Now, obviously, that was in a different country where the rules are different for flying, and that was permissible there. And we hope that in the near future, that out of line of sight flying for nuclear emergency response applications would be just as allowable in the UK. And we use sites like Fenswood where we can fly out of line of sight, certainly a big enough site. It's testbed sites like this which allow us to prove to regulators that we can do it safely. Peter's actually showing you on the video, which was very helpful, the kind of snail trail data that we've got coming in from the system. So this system is transmitting at a 1 Hertz rate. So we're getting in radiation data every second from the system. And it provides us with information around the intensity of the radiation. And obviously, essentially a snail trail is lots of point measurements made one after another. So as we fly the system around, in fact, usually we fly it completely autonomously, so that all we'd be doing is sitting and watching the incoming data. We can see the data as it's formed as a map. And you can see there's a hotspot somewhere in the middle of that map that's showing there on the screen. And what we can then do is, once we've seen a hotspot, we can send the drone in and we can go slower and we can go lower, and that helps to refine exactly where the hotspot is located. So once you've got to that, you can then switch to the thermal imaging capability, which is a different wavelength of radiation effectively, and you can start to correlate whether that radiation hotspot matches with a particular object or feature that's on the ground. And of course, in the instance that we're showing you here, what we can see is a metal ammo box, which is actually filled with rocks which have been collected from parts of the UK, which are naturally radioactive. So this is not a strong radiation source, but it's strong enough that our system can detect it quite easily. And of course, when you switch to thermal imaging, it sticks out like a sore thumb, because it's a metal box in a big grassy field. You can't actually see it when it's out in the field because the grass is too high, But of course, when you fly a drone directly over it, you can of course see that, not only in thermal, but with the HD imaging capability. And there's 3 cameras on the system when we fly it, and you can switch between them intuitively as you want as the pilot, which is really good. So once you've found a radiation source on the ground using this technology, then it's actually convey those coordinates to Mark, for example, to send in a ground robot, which would then go and investigate in much more detail and potentially take the object away and do something with it safely.
Wonderful. Thank you, Tom. Right, I'm going to leave you alone for 10 minutes so you can go set up. And I'm going to see if just have a chat to Mark. Mark, do you want to overview what you're going to demo today?
Yeah. Let's talk a little bit about what we're doing in NCNR. And I have a few slides that I can talk you through briefly. Our focus is that we are really here looking at closing the loops. We're closing the loops between navigation and manipulation. So we're talking about mobile manipulation to be able to go about these sort of environments that we've just seen. And we will also see that we're closing the loops between reality and simulation, because in particular, when you deal with radioactive environments, we don't really want to have lots of radioactive sources around in our environment. So we've actually worked quite a bit to facilitate also the development of digital twins. And we're keeping also closing the loop between humans and robots. Because especially in a domain like nuclear, you really want to have the experts in the loop. So which is why there's a lot of effort also in teleoperation. So we're going to talk a bit more about that and see some simple examples of that. I'm moving forward a little bit, and you will find that what we are doing also at Lincoln is not only nuclear robotics. We have also a lot of effort and lots of works going on in the agricultural domain that you may already have heard about, while we're doing a lot of work in strawberry picking, phenotyping in fields, etc. And we're using a same platform as the mobile base here, and a lot of the technology is actually shared, because while nuclear is an extreme environment, and so is agriculture. Well, the whole story here is, if you look at the little video that you've seen before, where we had a drone doing a reconnaissance mission of an outdoor field, we can do the very same also with a mobile base that goes about in a field as we see it down here. This is more from our agricultural campus, and I'm just going to say, like, there's an interesting link between these two domains for us that we're really trying to exploit. And this is a link between a simulation, a gazebo simulation that you see here on the left, and the real world environment. No, sorry, no, you see the simulation on the right, and a real world environment that you see in this little video here. And the concept is really that we can just populate the virtual world, which is linked to the real world, with some artificial information, which is a really powerful tool overall to do a lot of these experiments. What we're showing here is basically a Gaussian process, as we call this, which does mapping and actually is able to find the specific items that are out there in the wild. Of course, that also works indoors. We've just done it outdoors because it's slightly more interesting, if you want. What we see here on the right is also this sort of then autonomously exploring this. So rather than steering it around, or we've seen this kind of drone being flown around, if you've got a large environment and you actually need to explore it, you want to have a robot that does it all by itself. And so we've done a lot of work in that context, which is called next best sense planning. Really, we're trying to optimize where these robots go in order then to come back with the highest fidelity overall radiation map, which will then inform the next step of where you go and what is the most important item that you then needs to pick up, sort away, and in order to eventually clear out an entire environment. Now, that doesn't have to be outdoors. As I said, this is often also indoors, and in particular when it comes to post-operational clean-out in nuclear domains, it's important particularly to be able to go about and basically put things in bins. Now, talking about putting things in bins, that's our next step. That's what we will be doing next. A mobile platform that can go about and can autonomously navigate in any environment, linked with teleoperation with haptic feedback. And we've done this sort of teleoperation within NCNR in different settings already. Here's one on the video where you can see one of our colleagues operating a haptic feedback device and then tidying up over a long distance where a secure link our lab effectively. So I'm going to take now my iPad and be able to show you around a bit more of what we are up to. So here's our robotic platform. We've got a bin, we've got an arm, we've got an operator. Imagine this operator could also be sitting somewhere quite distant away. We're not showing this right now, but there's a lot of work also in augmented and virtual reality in order to provide a very immersive environment so that people can actually really over long distances see and be immersed into the operational environment where this robot is probably in an environment you don't really want to be at. So what we're going to do now is Soren is going to navigate the quite big platform, and which is currently, because we don't want to have any mess up with our Wi-Fi connected with wires here, and pick up this really dangerous item that you see down there. I'm not going to get close because it's virtually radioactive. All right, let's get it moving. Of course, as you can already see in the background, there's also some strawberries, because just before we've done actually some strawberry picking with a similar setup here, where also this arm is being used. And now we can see Soren actually operating this Franka robot over there, basically using it as a very fanciful joystick, which gives him also force feedback. So he has a very dexterous ability to manipulate objects. So not just these kind of simple boxes as this one, but also can actually manipulate much more complicated objects and can actually feel what they are like. So that's one of the key ideas here. And we're also doing some work. You see these kind of nice markers on top of it, where we're doing some haptic guidance in order to, again, support the operator to really be guided towards this object so they can manipulate this. Right, the box is in the bin. That's the key bit that we have to achieve. And then, of course, the platform can carry on. And we can actually carry on also with this sort of mapping as we've seen before. Right? So now we have removed something. We can start mapping the environment again, you know, to find the next best thing, or the next most important thing we need to actually look at.
Mark, do you think you could show us somebody moving the arm, just to show how the arm?
We'll show you moving the arm in the sack. So, you know, first step is always that we get the base close, and then the idea is really here. So here you see Soren actually using a Franka robot that is here and using it as an immediate mirror of this setup. And what this direct mirror basically allows, that he can actually operate and use this Franka as a fanciful joystick that gives him also haptic feedback, so he can feel whether he's actually hitting something, whether he's grabbing something, and that gives him a much more dexterous and immersive experience in order to be able to manipulate objects that are not quite as nice as this one. The key aspect here is also that we use also haptic feedback, not only directly from the physical world, we can also generate virtual forces. By knowing where the object is being directed to it, the operator can feel also to being guided towards picking up these sort of objects. I can give you a quick round through the lab because we do a lot of other bits of research. So there's an autonomous forklift truck. We're doing quite a bit of in logistics. You've seen the sort of areas of agriculture, where it's like strawberry picking is a big part of it. We've got this sort of teleoperation and in general manipulation setups within the National Center for Nuclear Robotics. We work very closely also with our colleagues in Bristol to work on augmented reality and virtual reality to give operators like this gentleman a bit better immersive experience. And then, of course, for all these sort of supported or shared autonomy concepts, you really need also the ability to plan for manipulation autonomously, so that we can actually decide which configuration should the arm go into to pick this object, so that we can then support the operator to follow a trajectory that actually will be successful.
Wonderful. Thank you, Mark. And that's a fantastic looking robot though, isn't it? I mean, it just looks like it's very capable to go off-road and really go outside of the lab.
Yes, it definitely can. As that we used this in many different environments already. It can conquer our Lincolnshire muddy fields and also the sort of steep inclines we are facing. So together with some algorithmic development about terrain assessment to be able to actually assess which routes, which parts of a map you can traverse with such a robot, that allows you to then also go into unknown environments, right? We're building the map and on the go, and can also navigate certain challenging environments that may actually be the result of some disaster and not just a nice wheat field as we've seen.
I think the same question applies to you as well, is how far away can you be from your robot, and what problems does that actually cause you?
Yeah, it's the question of of actually communication range in that sense. So there's two answers to that. On the one hand, we operate robots autonomously out there in the field almost all the time, in have a test bed for 5G to actually see what sort of high bandwidth operations we can do. So we regularly operate robots from here that are actually about 100 miles away. So that's not so much the problem for these autonomous robots. Of course, if there is indeed a nuclear disaster of some sort, that could well have massive impact also on the communication infrastructure and interference you would have on site. So that's when it really becomes important that you don't just have teleoperation, but you also have autonomy. And that's where, if you have seen these sort of things before, where you need to autonomously explore an environment in order to then also be able to know where you may have higher levels of radiation, which prevent any direct or good communication, and to go somewhere else in order to overcome that.
So do you feel in the future that these systems will work alongside each other? So Tom's technology with the drone will be able to find radiation sources, and you'd be able to send in ground vehicles to go and interact with those radiation sources?
Yeah, of course. That is I think one of the key bits. And so you see more and more of these sort of systems approaches, where a drone has clear benefits when it comes outdoors, and we can get a initially probably relatively coarse overview map, but it highlights it. You can even start building an a priori map of the environment that you then refine by actually going into that. There is no real problem in order to bring this together, other than at the moment, due to, we all know the challenges that we face at this current time, that we just haven't been able to share the same environment and actually tried it out on the same place.
Hi, Tom. I can see you up in
Hello,
there.
Pete. I feel like I'm a sort of BBC broadcast journalist right now, because you probably got the background noise of the drone. You can hear it's quite an angry bird.
I really envy Tom. Being out there. It's much nicer.
when we practiced this before, the weather was horrible. So,
but now I envy you.
Lady Luck's been smiling on us today. So I'm actually just going to bring the drone over for us a second. And Pete, just tell me if the sound gets really terrible as it gets closer, because I want to avoid that. Hopefully you can see the drone coming in just behind me now. We've got a full HD camera gimbal payload, which is the thermal imaging. And then we've also got the radiation mapping system, which just sits just underneath here on this side. Now that's transmitting its data live, and really importantly for mapping radiation, it's got a downwards facing ranging LiDAR with 120 meters of range, which allows us to get height above ground, and that allows us to calculate the on the ground radiation from up in the air, which is really very important. And if Suresh just shares the screen from the Navigator's app, you'll be able to see that we started to form a snail trail. I'm just going to hold it up. And now the important thing there is that's tracking exactly where the drone is at any one point in time. And you can see that there's a color that's proportional to the counts. Now, the counts at the moment are really very low, and that's good because I'm not expecting a big radiation spike today. But of course, what the system does is it auto scales. So if I did encounter something that was really radioactive versus the natural background, it would very quickly scale that for me and show it as a nice bright red dot, whereas all the other points would be green. At the moment, we're at a count rate of about 81 counts per second, which is, trust me, it's normal for Bristol. Bristol's not that radioactive. But typically when we're flying at Chernobyl, we're talking of thousands of counts or tens of thousands of counts per second, and it's really very obvious. But yeah, this is the drone system. You can hear it's quite noisy, as it should be. And I'm going to just take it off for a little bit of a test flight now, take it out over the fields.
How does weather affect you? Because we've got a comment saying, beautiful day for drone flying. What is your limitations? Is there a limitation on wind speed or rain? Do you have an IP rating? Can you take rain?
Essentially, it's an aerial park at the moment, which is quite a nice place for it to be. And it will stay up for about 55 minutes for this platform. This platform is specifically created for emergency response applications. So it has an IP rating, which allows it to fly in the rain, which is great. And it can fly in reasonably high winds, but not sort of tornado force winds, but sort of wind speeds of around 15, maybe 20 miles per hour. It can cope reasonably well. And that's because it's quite a big, heavy, powerful system. And certainly a lighter be able to sort of do this. So that's the reason why we've selected this platform specifically to integrate with, because it, versus any other drone system, really it has the best capability for flying on most days, not all days, but many more days than you could for most other drone systems, certainly.
Okay. I've got a similar question for Tom and Mark, is that during this pandemic, what did you do when you couldn't get into the labs? What did you do when, instead of doing these live tests and experiments?
Tearing my hair out.
Yeah, it's all gone. It's all gone. But I mean, COVID's been a real challenge, but what it has taught us is that we can achieve a lot by using, Zoom, Teams, whatever the platform, and that you can do virtual hackathons in many ways. We've been fortunate in that we have an outdoors facility and capability, which has meant that we've been able to, certainly with development of this, being able to quickly get things out into the field, either on your own or in a socially distanced pair, to do the necessary testing and development. But one of the first things I did within lockdown was to get my team and myself to get all of our sort of electronics kit to people's houses, and things like 3D printers, set up a 3D printer in my study so that we could go through the stages of rapid sort of iterative prototyping very easily without having to be in a university lab. So, some of it we literally had to sort of work out as we went along. But I think we've all achieved within the consortium a lot more than we thought we could, given it was a global pandemic.
Yeah, indeed. I mean, we're also lucky in that sense that we've got quite vast outdoor spaces on our campus that we could do some of the outdoor bits in robotics. But indeed, the development of digital twins and simulations has advanced significantly over that time. And that does pay back to some extent. We didn't have that technology initially because, of course, people find it much more exciting to get on their hands on the real robots. But in order to actually, allow also students to be educated in it, we make much use of simulations, much more use of simulation than we did before.
As Peter said before, one of the questions is how high a wind speed can the drone fly at? Today's wind, I think, would probably is something like 15 miles an hour. It's absolutely fine in these kind of wind speeds. It will go up to much higher wind speeds as well. So although it sounds windy, it's perfectly all right for drone flying.
We've got another great question, actually, which is when you're teleoperating this vehicle, or the vehicle is working autonomously and you're teleoperating that autonomous action, what happens when you lose communication? When you lose communication, does it just go mad and start driving into a wall and smashing everything up, or is there some fallback operation that's in place?
Right. So obviously, when it comes to navigation outdoors, all of the, let's say, obstacle avoidance, all the safety bits are on the platform itself, so it can navigate even if it has no connection. And a lot of the work we're doing is about autonomous operation. We've been sending out these robots far away into fields where they lose contact to the probably only 2G network ever so often, and they still do their jobs in there. So in terms of navigation, that's relatively easy. What you lose if you lose connectivity and communication breaks down is at the moment the teleoperation part, right, where you want to actually have a very, very low latency communication between your operator that sits there. Can't do this properly. There we go. and the arm. So that is a functionality that would break down as it is at the moment. We've got within NCNR also people that work particular on resilient electronics. So that look at the aspects there, how you can actually make electronics that are resilient even to high levels of radiation. That is something that if you want to really go out with something like this, then you need to work on that. That said, while teleoperation and shared autonomy teleoperation is brilliant and is actually something that the nuclear sector is extremely interested in because they really want to have the operator in the loop, a lot of the competence to actually do autonomous grasping has also been developed within the context of NCNR, mostly also to actually support the operators in it, so to guide them. So, if you're going to do something like shared autonomy and you want to guide a person operating a robot remotely towards an object, you already need to understand of how you want to grasp it. You need to actually have a plan for the trajectory to then use that information to guide people. So in that sense, it's quite in some ways, it's often easier for us to say, like, oh, we're just going to do autonomous grasping of these sort of objects. It becomes tricky if you've got objects that are very, very odd-shaped, very strange physical properties, extremely unknown, and that's where some of the kind of fully autonomous grasping challenges come into the play. So I can give you another kind of, I mean, is that we've just inspired by the strawberries right there. Is this sort of, if you have them and in growing in bunches, and you want to pick one specific one out, you need to push the others away, and that's another sort of extreme challenge you also face if you have a heap of nuclear waste that you need to sort out. So that's why we've done a lot of work also to learn how you actually can push a heap of bits autonomously out of one another. So you learn how to actually segregate this so that you can see the individual objects and then you can pick them autonomously. So you can do those sort of things in communication failure. It certainly won't go mad and won't crash into things. That's not going to happen. But indeed, low latency, high bandwidth teleoperation, fully immersive with an operator 1,000 miles away is going to suffer.
Yeah, and a very, very good point. And I think the point you made is that this is research technology. So Professor Mark Anheider and Professor Tom Scott and all the other professors and researchers within the National Centre for Nuclear Robotics, they are working at the cutting edge of what's possible. So not always is it reliable, not always is the system fully built as perfectly as you might expect to see. But what we're doing, is proving that through their advanced algorithms, vision systems, control systems, network communications, that we're actually pushing the boundaries of what's actually possible. And then the hope is that companies and industry take that technology and run with it and actually build it into a product that's actually retailable. Now, again, thank you, Mark. Very, very well put. Just a question that came in the comments. I believe you answered it in the comments, but just for those that are listening to audio only or just watching the video, how long does your mobile platform actually run for? How far can it go, and how long can it go for?
It really depends on what you want to do. So when I said, I wrote in the comments 8 hours, and that is a mean value with a massive variation in it, because we use this platform, for instance, with our colleagues in something like UV treatment, high intensity light treatment of crops, and that high intensity light treatment means it takes just 2 kilowatts of light, just where the energy goes in that you can't run for 10 hours and the batteries are drained, but you can also just put more batteries on. So really scales. I would say our normal, when I say 8 hours, that is the kind of typical operation environment that you've got. If you do something that is high intensity work, like shining high intensity light or something, then you get less. If it's just moving in even terrain for a little bit, you can easily reach 60. And then it depends also on what sort of batteries you chuck in.
Put the drone on a table behind me so you can see it, rather than it hovering just over my head, making a really annoying noise where nobody can quite hear it. And also looking at the laptop screen, flying the drone behind me. That was a new one. I'm not going to do that again for this next session.
I'm sure that you had somebody with you to be your spotter.
I did. I had Suresh. He had the navigator's handset, and with the navigator handset, you can take over. So,
so if anyone from the Civil Aviation Authority is watching, we were safe.
Yeah, exactly. And super safe now because it's powered down, just sitting on the desktop. So we did have it flying solidly for about 55 minutes, which is the sort of max capability for the drone. And of course, in 55 minutes, you can fly quite a long distance. I mean, this system itself at full speed, you can be traveling at 60 mile an hour or more, so it's quite fast when you want it to be, and so you can go quite a long way. I've got to keep it on the ground for a little while longer because it's been flying for about 55 minutes, which means it needs to physically cool down. So I got a partial warning on the system as I landed to say it's hot. I need to cool down for a bit, which is quite useful to have that capability. If we were flying it in it overheated, what it actually does is it just returns to its takeoff point and lands itself autonomously, which is quite helpful.
Just a quick question, Tom. Somebody asked what's the minimum size or intensity of radiation hotspots that the drone can identify? And I don't know how you answer that question because size and intensity, I don't know how they overlap.
Yeah, it would be intensity really that you're looking at. So we know with this system and in particular, which is using a cesium iodide detector, that we can spot sources which are something like 50% or maybe only 25% stronger than natural background. That's quite easy to distinguish. So for example, in the test that we've been showing on the video, that is literally 3 rocks about this size in a metal box, and those rocks are being collected from the Cornish Peninsula, if you like, and so they represent what we call norm sources, naturally occurring radioactive material. So they are extremely weak versus the kind of stuff you get on a nuclear site. And part of the reason that we test with these weak sources is because you actually need your system to be able to pick up very small anomalies, because you want to catch things early, really. Interestingly, though, when we did our NCNR work in Chernobyl, in the Chernobyl exclusion zone over the Red Forest, you could have flown this system at over 300 meters above the ground. In fact, I think it's 350 meters above the ground, and the detector would still be saturated. That's how radioactive it is there.
Wow.
So what we had to do in the field there, which is with a slightly different system, because it wasn't with the DJI M300, we were using an M600, is we had to change sensors in the field to one which was much smaller so that we didn't saturate it. Because probably if you went to the wrong part of the Red Forest and decided to camp overnight, there's a chance you wouldn't be alive in the morning because of the radiation levels.
Just another quick question from the comments. Mark, Tom said his drone will go about 60 miles an hour. There's just a question: how fast will your vehicle go? Can you keep up with him?
No, I don't want to keep up with him on the ground. With that, no. I mean, as general, air traffic is faster than ground traffic. We could probably do 10, but I don't think we would.
As I say, slow and steady wins the race.
The point being, Pete, is I can cover a lot of ground quite quickly so that Mark doesn't have to. He knows exactly where he needs to go, and he goes route 1 straight to it.
Very true. So
but
indeed,
I can operate longer than he can.
Yeah.
He'll probably cover the same distance in total.
That's a very good point. That's a very good point. That Tom can quickly survey the whole area, which allows Mark to go as the crow flies directly to that radiation source.
And
okay,
in fact, we've got another drone up in the air at the moment. I don't know if you can just make it out. Over there.
Yeah.
Yeah. So we've got 2 M300s at the moment. One flying and then one directly behind me.
Wonderful. Thank you very much, everybody. We've only got 10 minutes left to this live stream, but I just really want to say thank you to everybody here, Suresh, Ricardo, and Professor Mark Hanheider and Professor Tom Scott. I think they all put on a fantastic demonstration. It's extremely hard to get these systems to work in a lab.
Don't forget the expert operator, Soran.
And Soran, yes, I'm getting Soran, because you've done a fantastic job at picking up that object, and you've obviously spent many hours learning.
He didn't drop it once the entire time.
No.
I mean,
so if there's a nuclear disaster, we want to send you guys.
You'd want Sarong and Suresh, because they're the guys who do all the heavy lifting on these types of projects. To some extent, us academics come in and communicate what we're doing and take all the glory, but actually all the credit is due to these guys, because it's, weeks, days, months of hard work to get to the point where we can confidently demo systems indoors and outdoors. So it's a big thank you from the academics to their research team, I think I would say.
Couldn't say it any better. Not going to repeat it. Yes.
Definitely. These guys these men and women spend hours and hours and hours in the lab, usually throughout the nights and throughout the days. And especially when professors or people like me say, can you put this demo on? And then they have to work even more hours on top. So we are very appreciative to the time that you spent on that. I think everyone's done really well. As I say, it's difficult to get these systems working generally, let alone getting them to work in the middle of a field or on the spot 4 times for a live demo. So I think you guys have done absolutely fantastically. Any other information that you'd like to put out there to the wider community about your lab and where they can access more of your work?
I'm going to say a few things. So first of all, Lincoln Center for Autonomous Systems. We do a lot of different research in the area also of agriculture, as we mentioned, logistics. We are also having a CDT. So if there's any people out there that are considering doing a career in robotics in the wider sense, in agriculture, and specifically, you want to look for the CDT Agri Forward. That is a center for doctoral training. If anyone wants to do a PhD with us, or with Cambridge, or with East Anglia, because they are our partners in that particular CT, which is about agri-food robotics.
Yeah,
Yes,
I'm at Fenswood Farm, which is one of the nodes of the National Nuclear User Facility for Hot Robotics. It's also where we've got a new aerial robotics MSc starting in September, but it's a great place to come and do and develop field robotic systems. So please do look that up. University of Bristol, Bristol Robotics Lab. We will be travelling back out to the Chernobyl exclusion zone in September. We'll be doing some deployments of UAV systems again. Please do pay attention to the NCNR website and also to our sort of LinkedIn feeds as well, because there'll be videos that we put up throughout the trip, which is about 2 weeks, which will be videos of robot deployments in the exclusion zone and, in fact, inside the new safe confinement and inside unit number 4.
So as Tom says, we have our website ncnr.org.uk, so please check that out. That will be updated soon with these videos and a number of other videos. I'd also just like to thank from my side, I've had a lot of technical support from Rui, who's behind me, behind this screen, who's helped me set up all these screens and streams and networks. So I'm very thankful to Rui for that. In September, we'll be doing some demos. So all of the systems developed through National Centre for Nuclear Robotics will be demonstrated in September, and we'll send out some information about that. So please look at our website towards September for an update on those systems. And again, thank you to everybody who's joined us today.